Hey folks, hope you guys are doing well today. We've been working a lot with rationals, simplifying rational expressions, multiplying, dividing, adding, subtracting, complex, and then solving rational equations. Well, today we're going to start working towards their graphs. And whenever we understand what's happening with a graph of a function, it helps us do those other things even better. And we're going to look at some of the key features today of our graphs. As we build towards being able to just give you a function and then you come up with the graph. So remember that a rational equation, a rational function has a numerator and a denominator where both are polynomials. So what I have typed in right here, okay, is a quadratic in the numerator and a cubic in the denominator. They're just already factored, okay? And let's talk a little bit about domain first. You guys are pretty good at recognizing here when we take a look that 1, 3, and -3 are not in the domain of this function. But what does it mean when it comes to the graphs? Okay, so let's take a look. I'll turn this graph on and we'll see what we notice. Okay. All right. Well, when I look at this, the first thing I notice is that there are two vertical asymptotes. There are vertical asymptotes at x equals -3 and x equals +3. Okay, let me graph those. X equals -3 and x equals +3, but I don't want them to be solid lines. Let's change these to be dashed. And let's make them both green. All right, so those are the vertical asymptotes at 3 and -3. And we see that looking at the denominator, 3 and -3 make the denominator 0. They are vertical asymptotes. But remember that 1 is also not in the domain. Is there a vertical asymptote at x equals 1? No, there isn't. What there is a hole in the graph there. Okay, 1 is undefined. Okay, and there's a hole. We call that a removable discontinuity. Discontinuous just means the curve doesn't continue. Something happens to it. It's a removable discontinuity because it's like that point was just removed, like it was plucked right out of the graph. Okay? So why the difference in those two features? Why did 3 and -3 make vertical asymptotes where 1 makes a hole? All right. Well, you may notice that 1, okay, has this factor x minus 1, which is also in the numerator, and they cancel out, which means if I put 1 into this function, I get 0 in the numerator and 0 in the denominator. That's called indeterminate. Whereas if I put in 3, my numerator ends up being what? 3 minus 1 times 3. It ends up being 10. 10 over 0. So that's the difference here. We end up with a hole where a factor is both in the numerator and denominator. We get 0 over 0 indeterminate, where we get vertical asymptotes when it's undefined, when the numerator is not 0 and the numerator is 0. All right? So those are the key features that we're going to be looking at today, are vertical asymptotes versus holes. And then we're going to look at one other feature as well, but let's just stick with the vertical asymptotes and the holes. So remember, a rational function, okay, is a fraction where the numerator and denominator are polynomials. Now, of course, the denominator cannot equal 0. Okay. Vertical asymptotes versus holes, also called removable discontinuity. So if our rational function is p of x over q of x, vertical asymptotes happen, I said, where the denominator is 0 and the numerator is not 0. So I say vertical asymptotes occur when q of x equals 0 and p of x does not equal 0. Okay, that is called undefined. Holes happen where q of x and p of x are both 0, where the numerator and denominator are both 0. That's called indeterminate. Okay? So that's what we're looking for. So let's find all the vertical asymptotes and holes, or removable discontinuities, of these functions. So the first thing we want to do is we want to factor them. Numerator does not need to be factored, but we can factor an x out of the denominator. So what values make the denominator 0? 0 and -10. Now we need to determine which are vertical asymptotes and which are holes. Now notice, there's an x here that gives us the 0. There's also an x in the numerator. Okay? Those cancel, and they create a hole. Okay? 0 makes the numerator and denominator 0. So x equals 0 is a hole, or removable discontinuity. X equals -10, though, does not have a matching factor in the numerator. Okay? It gives us -40 over 0, which is undefined, and this is a vertical asymptote. And if you're okay, I'm going to just abbreviate that VA, vertical asymptote at -10. Okay? Let's look at the next one. All right, let's factor. Denominator is x, what would that be here? Plus 6, x minus 4. Let me double check. That's our -24. 6x minus 4x is 2x. What makes the denominator 0? -6 or 4. Does the x plus 6 have a factor in the numerator where it would cancel out? No. Okay, so that's a vertical asymptote. Does 4 have an x minus 4 in the numerator? No, it doesn't. Okay, this is also a vertical asymptote. Now, sometimes I have students say, well, what about x minus 3? Is that a vertical asymptote or a hole? Good question. What happens when we substitute 3 into this? I get 3 minus 3, which is 0, divided by 3 squared plus 2 times 3 minus. It doesn't matter what the denominator is. When I put, it's not 0. I should say that. Doesn't matter. It's non-zero. Okay? So when I put in 3, I get -0 over something that's not 0, which is just 0. So what is x equals 3? It's not a vertical asymptote. Okay? It's not a hole. Okay? It is and it is an x-intercept. When I put 3, f of 3 equals 0 means we have the point 3, 0. It's an x-intercept. So a little side lesson here. Where the numerator is equal to 0 and the denominator is not, those give us x-intercepts. All right, let's keep going. How about this one? This one we need to factor the numerator and denominator. And this factors to be what? X plus 5, x minus 2. So this has 3 places that make the denominator 0. All right. How about x equals 0? Does not have anything to cancel out with the numerator, so this is a vertical asymptote. -5 does not have a matching factor in the numerator. It is a vertical asymptote. But x equals 2 does have a factor there that it would cancel with. So that is a hole. Okay. Now how about -2? That would be an x-intercept. All right, but I didn't ask for those. All right, so hopefully you guys are doing fine with that. Okay, now let's take a look at the function 1 over x. Okay. Now we should know what the function 1 over x looks like. It's in our parent curve book that we've created before. Okay, it looks like this, and it looks like that. And we would know that x equals 0 is a vertical asymptote. It's usually the first thing that we notice. Okay? But what sometimes we miss is that this has another type of asymptote instead, a horizontal asymptote of y equals 0. Okay? And graphs can have horizontal asymptotes as well. So, like, even look at this one that we started with. Did you notice that y equals 0 is also a horizontal asymptote? It's a line that the curve approaches and gets closer and closer to as we move further to the right and the left, as x goes to negative infinity, as x goes to positive infinity. All right? So we end up with these horizontal asymptotes. And what I want to do is I want us to just play around here a little bit with graphs and see if we can figure out, when do we end up with a horizontal asymptote? Now let me delete some of this. So both 1 over x and the graph that we just looked at had y equals 0 as a horizontal asymptote. Let's just make up something here. How about x squared plus 4x minus 3? That was not a 3, there's a 3. And how about x squared plus 2x minus 1? Okay. Does this have a horizontal asymptote? Is there a horizontal line that the graph approaches as we go towards x equals negative infinity and x equals positive infinity? Well, one way for us to kind of help see that is to just zoom out. Okay? And if I zoom out, do you end up seeing a horizontal line here? I see one right there. There is a horizontal asymptote for this one, and it's y equals 1. Okay? It approaches from the bottom over here. Up here, it approaches from the top. Now, is it okay for a curve to cross a horizontal asymptote? Yes. It can come up, cross it, and go back down. That's just fine. Is it okay for a curve to cross a vertical asymptote? And the answer to that is no, right? If I have a vertical line and if I have a curve that's crossing that vertical asymptote, it's no longer a function, so we won't see that. But we can see it, a curve cross a horizontal asymptote. All right, so this has a horizontal asymptote of 1. Now, what if I make this a 3 up here? No longer does it have a horizontal asymptote, right? Same as if this is a 4 or a 5. No horizontal asymptotes. And why would that be? Well, if we look at these functions, and I want you to kind of think about the numerator and denominator are in a battle to see who wins. All right? When we take a look at this, the numerator has an x to the 5th, where the denominator just has an x squared. An x to the 5th is going to grow a lot faster than an x squared, right? If I put in 10, 100, 1,000, 10,000, 100,000, the numerator is going to get bigger faster than the denominator because that's to the 5th power while this is only squared. While both the numerator and denominator are going to start to get really big numbers, okay, as x gets bigger, the numerator is going to get bigger faster. It wins the battle, and that sends our graph off to infinity. Okay. Now, what would happen if I were to reverse these? Let's make that a 2nd, and let's make this a 5th. Here we have a horizontal asymptote of 0, because this time the denominator wins the battle. If I have a fraction, and the denominator is getting bigger faster than the numerator, what's happening to that fraction? Okay, let me just give you an example where I'm going to make the denominator, I'm going to make both the numerator and denominator bigger, but I'm going to make the denominator faster, bigger faster. So let's start with 1 over 2. I'm going to make the numerator bigger, but I'm going to make the denominator bigger faster. I'm going to do that again. Let's make the numerator bigger, but the denominator bigger faster. Numerator bigger, denominator bigger, faster. What's happening to this fraction? Well, it starts at 0.5, then it goes to 0.1, then 3 200s, then 4 2000s, 5 20,000s, 6 200,000s. Those numbers are getting closer to 0. The denominator is winning this battle, and it's making the fraction get smaller and smaller and smaller and closer to 0. If the degree of the denominator is bigger than the degree of the numerator, the denominator wins, and it goes to 0. If the degree of the numerator is bigger than the degree of the denominator, the numerator wins, and it goes off to infinity. So let's keep, checking those. Like if this was a third degree, it still has a horizontal asymptote of 0. The denominator is still winning this one. Okay? But if the denominator is a 3 and the numerator was a 6, the numerator is going to get bigger faster, and it's going to go off to infinity. But how about that situation, okay, where we had that horizontal asymptote at y equals 1? Well, we've talked about the numerator being bigger, the denominator being bigger, but what's the only option we haven't talked about? We haven't talked about if they're the same, if the degrees are the same. So here we have a third degree on the top and a third degree on the bottom, and this has a horizontal asymptote at y equals 1. Here's what I want you to think about. As I look at this function, as x gets really big, and I'm not talking like 70, I'm talking like 70,000. I'm talking about 7 million. As x gets really big, do you think this minus 3 and this minus 1 is going to have a major impact on the value of the numerator and denominator? If x is a million cubed plus 4 million minus 3, are you going to notice that minus 3? No, you're not. Same with this minus 1. So let's just ignore the minus 3 and the minus 1. Well, even with these x's in here, we're talking about 1 million cubed. 1 million cubed. A million has what? 6 zeros. So when you cube it, it's going to have 6, 6, 6, 18 zeros after it. Is an extra 4 million really going to make that big of a difference anymore? No. Same on the bottom. So what I end up doing, okay, usually, and I just hold up my hand if I was on the board covering those, is I ignore everything else. And what do we end up with? X cubed over x cubed, which is what? 1. And where did we see that horizontal asymptote happen? It happened at, there we go, that's what I wanted to do, at y equals 1. Okay. Now let's make up another one where the degrees are the same. This time it's going to be 3x to the 4th plus, I don't know, a bunch of other stuff. And then let's make this an x to the 4th plus, I'll just leave that other stuff. All right, the degrees are the same. So what I do is I ignore the constants, I ignore the x's, I just cover everything up except 3x to the 4th over x to the 4th. And when I do that, as x gets really big, this stuff doesn't really matter, and this stuff doesn't really matter. We end up with 3x to the 4th over x to the 4th. And what is 3x to the 4th over x to the 4th? Just 3. So it really approaches 3. As it gets bigger and bigger and bigger for x's, the numerator is just about 3 times bigger than the denominator. And notice y equals 3 is the horizontal asymptote that this function approaches. So let's summarize. Okay, let's make a table here. Let n be the degree of the numerator, and let's let d be the degree of the denominator. So there's 3 things that can happen. The numerator's degree can be bigger, they can be equal, or the denominator's degree can be bigger. If the degree of the numerator is bigger than the degree of the numerator wins and it goes off to infinity. So I'm going to say no horizontal asymptote. If the degrees are the same, the horizontal asymptote is y equals, and I'm just going to write ratio of the leading coefficients. Look back at this one. Where did they go? Leading coefficients, 3 over 1, it was 3. Leading coefficients, 1 over 1, it was 1. If the degrees are the same, it's the ratio of the leading coefficients. Now, if the numerator is smaller than the denominator wins. And what was our horizontal asymptote? y equals 0. If the denominator gets bigger faster, the fraction goes to 0. Okay. So let's identify horizontal asymptotes. Take a look at number 1. 1 over x minus 3. What's the degree of the numerator? 0. There aren't any x's. The degree of the denominator is 1. The denominator wins this battle. The horizontal asymptote is y equals 0. Number 2. The degree of the numerator is 2. The degree of the denominator is 2. They're the same. That means ignore this stuff. Ignore this stuff. Okay, what does this approach? What is the ratio of the leading coefficients? 3 to 2. Y equals 3 over 2. 1.5 is the horizontal asymptote. All right, how about this one? Degrees of the numerator and denominator are again the same. What's the ratio of the leading coefficients? Negative 7/11. Y equals negative 7 over 11. This one, denominator's bigger, third degree, numerator's first degree. This one just goes to 0, denominator wins. Here, numerator wins, fourth degree to second degree. Where's this going to go? It's going to go off to infinity. No horizontal asymptote. It's going to go to infinity. So, vertical asymptotes, holes, horizontal asymptotes, a little bit of x-intercepts mixed in there. That's a good start to graphing. Okay, one more concept I want to talk about, and then we'll be able to start sketching graphs. Thanks for watching. We'll see you later.